announcements. First of all, Gambit C 4.0 has been released. It's still a bit Also, I released.
So let me clarify the title of the presentation. The 90 minutes is not the time to write the compiler, but to explain it. The goal of this talk is actually, or rather the motivation of the talk, is that several people have been asking me, well, how can you compile Scheme to C? What are the difficulties? Can it be done? You know, what are the problems, and so on. And they're not necessarily very complex. And I think that in principle, 90 minutes should be enough to present the major problems in compiling Scheme to C. So this presentation is not about Gambit C. It's about a new compiler called the 90-minute Scheme to C compiler, which is about 800 lines of scheme code, so it's not very big. It actually does all of the difficult things of compiling Scheme to C. So the goals are to explain how Scheme can be compiled to C, to give you enough details to do it at home, if you're so inclined. I actually have the source code that you can also take off of the web if you want to experiment with that. So I want to try to explain all of this in about 90 minutes. Of course, I wouldn't be able to go into the detail. My original goal was to actually do a source code walk to go through all the pieces, but it just won't happen. So non-goals of this compiler is to be RNRS compatible. It's actually a reduced subset of Scheme that is sufficiently powerful to actually see how you could implement continuations and that kind of stuff. But it's not in any respect close to compatibility with any standard. Nor does it do anything about C interoperability or anything like this. It's really how can you translate a Scheme program into a C program. No optimizations, performance has never been a goal. And I want to explain optimizations and implementation of Gambit C and so on. So you'll appreciate this talk if you are a coder, if you like code. I'll be showing a lot of code, a lot of sort of Scheme type code with continuations, higher order functions, and so on. So it helps if you actually know how to program with higher order functions. That'll be sort of throughout the presentation I'll be using higher order functions. So why is it difficult to compile Scheme to C? Actually, Scheme has a lot of things that are neat, that we like, and that C doesn't have. And here is a list. C doesn't have tail calls. Okay, and that's probably the most difficult thing to work around, is the fact that Scheme does have tail calls, and when you do a tail call, it has to be a tail call in Scheme. It can't take any stack space, any space in continuations. And in C, when you do a function call, you usually consume stack. So that's a problem. In Scheme, there are first-class continuations, and obviously in C there is no such thing. There are closures in Scheme and not in C. You could say that C++ has a kind of closure, or there's a way of simulating closures with the object system, but here I'm targeting C. Moreover, closures have indefinite extent, which means that if you create a closure somewhere, it can actually live for as long as is required by the program. So you could actually return a closure from a function, store it in a data structure or something like that, and essentially the garbage collector has to be in charge of reclaiming the closures. And finally, there's a garbage collection, which doesn't exist in C. So the implications of this is that we can't use C function calls to translate scheme function calls. And that's a big hit, because it would be the natural thing to do, represent a scheme function as a C function, use C function calls to call the scheme functions, and everything would be nice. But because of the absence of tail calls in C, we can't do that. So we have to find some way to work around that. We also have to implement continuations, first class continuations, closures, and we also have to set up the system so that garbage collection is possible. So we have to tackle all of these problems. And as I said in the end, the rest is actually easy, left as an exercise. Once these things are solved, the rest is well, it's a lot of work, but it's sort of manual work. So let's go through each of these issues and see what I mean. So let's look at tail calls and garbage collection. Here's a small function. Function of 2 and x. If n is 0, we return the car of the pair x. So x will always be a pair. Otherwise, we call f recursively, and we just decrement the value of n, and we pass a new pair here, which is the content of the critter of the old pair, and the sum of the current critter. So, can anyone say what this does?
Yes, sir.
So it's Fibonacci. It's just a weird way of writing Fibonacci so that you can see the problems. So here we have a recursive call to f, and because this is a tail call, this actually runs in constant space. So whatever the value of n, this will run in constant space. If you disregard the size of the numbers, because actually the numbers take a lot of space because the Fibonacci sequence grows very quickly. But if you ignore that, it actually has to run in constant space. Moreover, we're creating pairs here, okay? And the pair that's created for one function call is actually no longer needed for the next iteration of this loop here. So actually the pairs have to be reclaimed as the program runs, and there's only one pair that's live at any moment. So all of this means that this program runs in constant space. Let's look at the closures issue. In Scheme, functions can be nested, something that C doesn't have, and variables are lexically scoped. So we can have a function like this, add all, which will take a parameter n and a list, and which will just add n to each element of the list of numbers. So we use map. So we map over the list LST, and the function that we pass simply adds n to the element x. So here we have a closure. So this thing here is a closure that has to somehow remember what the value of n is so that it can apply it, it can add it to each element of the list. So if we say add all 1 to the list 10, 20, 30, we get this. If we add 5, then it will add 5 to each element. So just a little bit of terminology, which I'll use later on. So if we look at the body of this lambda expression, there are two variables that we're accessing here. X and n is actually a local variable, a parameter of the function. So we call that a bound occurrence of x. So actually the definition of x is actually in the function that we have here. And n is what is called a free variable. So it's a free occurrence of the variable. And it means that in the program, n has to come from some definition that's outside of this lambda. And this is what's causing the... Well, first of all, that's what the power of closures is. that you can do something like this, and it's also the problem. We have to find a way of actually transporting the value of n from the first lambda into the second lambda. So the last comment down here is just to say that when we access x, it's fairly easy to understand how we can do that. If we have a stack frame that says, well, we have the value of x on the stack frame, then the reference to x here is simply referencing a slot of the stack frame. It's the end here that's less obvious how to access that value. Another problem is the extent of the closures, that is how long they live. And closures can actually outlive their parent. So we can have a function, this is a classic example of makeAdder, a function that takes an integer n, a number n, and which will return a function which takes an x and will add x and n. Okay? So when we call makeAdder, okay, for example right here, we get a call to this function which will return a closure. Okay, so the closure actually outlives the activation of the parent, and then we get the closure inside here, which is then passed to map, and then this ends up adding a 1 to each element of the list. Okay? So we can't use a traditional stack allocation for stack frames, for activation frames, because if we the traditional implementation is that when a function returns, the activation frame is reclaimed. And if we do that, then the activation frame that contains n, okay, will be reclaimed when makeAdder returns. And then there's no way to actually get to the value of n. So the closure has to remember somehow the parent activation frame, and it's up to the GC, the garbage collector, to reclaim activation frames when they're no longer needed. Okay, another problem, first class continuations. So in Scheme, we have call CC, an operator that allows the programmer to actually access the continuation and then to arbitrarily, at any moment, return to that point in the program. I'm not sure how many of you are familiar with continuation, but I basically have a short explanation of the concept here. So a continuation basically denotes a suspended computation that is waiting to receive a value. And an example is the evaluation that you have here. If you type at the read-about print loop square root of the sum of the call to read and 1, when this is run, the call to read actually suspends the program, waiting for the user to input a number. So this really means you can think of the program as having a continuation, a suspended continuation, that is waiting for the value that read will return, and then this continuation will go ahead and add 1 to the value that it receives, and then compute the square root, and then print the result, and then go on to the next read-about print loop interaction. So that's sort of the basic idea of continuations. So call with current continuation, the call CC operator or procedure in C turns the continuation into a function. So continuations are actually implicit in Scheme, and with the call CC function, you can actually reify, make real this implicit continuation, and then use it in your program. And call CC will transform this implicit continuation into a function. And when you call this function, it actually will resume the continuation that it corresponds to. So here is a very simple example, and it's modeled on the previous example. I've replaced the call to read by a call to call CC. So here we're doing the square root of the sum of a call to call CC and 1. Call CC is a procedure, so it has a continuation, which is exactly the one we had in the previous example. Namely, that if we feed a value to this continuation, it will add 1 to the value, compute the square root, and the result, and so on. So what is happening here is that call CC, when it's called, receives an implicit continuation, and actually will call this receiver function that we have here with, as an argument, a function that represents this continuation. So inside of here, we can use cont as a function, and when we call this, we're actually returning to this point in the code, to the continuation of the call to call CC. So if we do something like this, multiply 2 by cont of 8, well, cont of 8, this call actually returns from the call of call CC with the value 8, adds 1, and the square root of 9 is 3, and that will be printed. So actually, this part of the computation isn't even used. This call never returns. So when a continuation is invoked, it's basically a transfer of control from one point of the program to another point of the program. By the way, if you have any questions, you can. So this is great for doing other things. Backtracking, coroutining, multi-threading, non-local escapes, all of these things can be done with first-class continuations.
Can read be implemented more easily using continuations?
Can what?
Read.
Well, read, I would say read can be implemented more easily, but you can implement a threading system more easily. So in fact, when read blocks on your device that's not ready yet, then your thread system could capture the state of that process by essentially getting its continuation, storing it in the process descriptor or something like that, and when the device becomes ready, the continuation is basically invoked. So it's not per se for read, but for the thread system, you can...
Okay, so it's easier basically with continuations to make read like thread safe or...
Well, what's easier is actually to express all of this within Scheme.
How do we call the continuation?
With a function call. So if you use a function call, so this cont here is a function. Okay, it's a function that you can use in your program, but it's linked with the implicit continuation that you have here. Okay. The call to call CC has a continuation. Okay, all functions that are called have a continuation, which is what remains to be done after the function returns, or once the function returns. Okay, so this is a function. Call CC is a function here. So it's called with a continuation, which is, as I said before, a computation that receives a value, adds 1 to it, computes the square root, and then prints the result. Okay, so call CC takes this implicit thing, this implicit continuation, okay, and actually makes it real in your program as a function. Here you can actually use it from this point on as the function count. And if you use it, if you call this function, then you're actually resuming this continuation, you're transferring control to that continuation, and computation keeps going from that point.
We need an example. If this is the example, I don't understand.
Well,
if this is complete as an example, I'm lost.
Okay.
Is it like set jump and long jump?
Yeah, I was just going to say that. So in C, do you use set jump and long jump?
No.
You can do threading with that.
Okay. Huh?
You can do threading and stuff like that using that.
Well, some people claim to have done that, but
Show the code if you want.
yeah. So
You're basically using the set jump. I guess what you're using is the set jump as the call CC. That sort of starts off and says, I now have the state, and then you start running in that state, and at some
Yeah.
point you use long jump to sort of jump out of that. What you're saying is that invoking the continuation is like exiting, and you exit via the call CC.
Well, there are very serious differences between set jump, long jump, and continuations, first class continuations. For example, continuations have indefinite extent.
Yeah.
Okay.
I
So if you do a set jump, long jump, if you do a set jump in a function, okay, and at some point this function returns,
Oh,
you can never go back there with the.
but there's ways of cheating that.
There are ways, yeah. But then you're mucking with this.
No, I totally agree. It was more a case of just trying to get this notion that you've got, it's not obvious what's capturing and what's invoking.
Yeah.
Yeah, I understand that you're interrupting something, you're in the middle of something, and you have that state, and then you use it. That's what I gather. What I don't gather is how does it. The previous example, the read, was doing something and then getting back and continuing. So I don't have. Is there an example of a delayed usage? You know, you get a state.
Well, I actually have some other examples that are coming up. that
Okay.
are much
Oh, wait.
more complex than this. But yes, you have to understand this before I move on. I've explained continuations to different people, and actually, different approaches actually work with different people. And one approach that I like to explain is to view the continuation as the stack. Okay, think of a C program or any program that's running. So essentially, you have state that is represented by your stack. Each stack frame represents some information that a suspended call, okay, the function that has called some other function, so that function is suspended somehow. Okay, so each activation frame is a suspended computation waiting for the result of a function call. And currently there's a current you're currently in one function that is active, but all the other ones are suspended. So the continuation, or let's say the implicit continuation would correspond to the stack, the content of the stack, and a return address. So once you have a return address and a stack, then that represents a continuation. Okay, you know at which point in the code you want to return the return address, and you also know what is all the information of the suspended functions on your stack.
Okay, that I have no problem with the example.
Okay. So call CC here, okay, is a function. So it is receiving a return address, okay, the point in the code where it has to return, and it's also receiving a bunch of stack frames, which represent, well, here there aren't many, but if you were deeply nested in some computation, then you would have a bunch of stack frames on your stack. And what call CC does is basically take a copy of that. That's another way of viewing it. You take a copy of all that, and you package it in a function. And when you call this function, the function actually copies the continuation back, the copied stack back into the real stack, and just returns to that point.
Call CC takes that picture, the stack, and feeds it into the lambda in that argument.
Yeah, I dislike the sort of the interface for doing first class continuation. You wonder why you need a lambda here. Why isn't call CC just a function that you call and it returns the current continuation at that point? There are reasons for this, but certainly the interface here is a bit weird. But what happens is that call CC is called with this function, and call CC will then call this function, passing this copied stack as this parameter. Okay. So you pass this function to call CC. Call CC does its bit of copying the stack and packages it up into a function, and then calls this with this function.
Okay.
Okay? So within this function, you're sort of logically still going to call CC. Then you can start doing things, and of course if you call that continuation, then all of a sudden you come back to the state you were in before. So here it's as though the call CC was returning with the value of 8.
Okay.
It's as though all of this had just been 8.
Is the const always use one argument, and it's the place where you're at?
It takes one argument because functions return one value. Okay. So here there's one value that is supposed to be returned by the call CC.
Okay.
That's the value that we pass here.
Okay.
I mean, that's sort of the simplified story because there are multiple values.
Well, I think it
and all
was
that.
more, as you pointed out, the interface that was mixing.
Yeah, the interface, I actually dislike the interface, and I proposed changes to the interface.
Can you show us what would be the interface you would like? Is it like...
Well, no. Because 90 minutes will expire very quickly if I start doing that.
What would be wrong with just getting rid of the lambda? Say call CC const and then...
So you're not thinking no as an answer, if I understand correctly.
What do you want to do with it?
I find the lambda superfluous.
So you want to turn call CC into syntax?
Yeah.
That's one proposal that you could have.
What would be another?
Or so. I don't want to get into this because it just adds to the complexity of understanding continuations. So here's a practical example of what you can do with continuations. You want to write a map inverse function, which will take a list of numbers and basically computes 1 over each number in the list. So map slash on 1, 2, 3 will return 1, 1/2, and 1/3. Okay. Of course, there's a problem in the case where the value, you have a 0 in your list, because dividing 1 by 0 is a divide by 0 error, and we want to give a special meaning to this. So if there is a division by 0, if there is a 0 in the list, we want the result to be false. Okay, so that's the specification of the function we want. So essentially what we want to do is traverse the list, and as soon as we find a 0, we want to exit the computation with a particular value, in this case false. And to make matters more interesting, or a little more complex, we're going to use map to do this. So essentially this is a map. We're mapping the inverse function over each element of the list. And this function will actually test if the value is 0 or not. And when it is 0, we want to escape. So what we can do is this. We call CC to actually get the continuation of the function map slash. Okay? And return here, what was called const before, I've called return here, is actually this continuation. So if I call this function, this is the return function, then it actually returns from this function. So within the body here, I call map, and the function that I pass tests if the argument is 0, and if it is, will return from the map slash function with sharpness. Otherwise, it just goes ahead and does the division, and if all goes well and there's no 0, then the list is returned. So this is sort of the simple example of what you can do with continuations, non-local escape, and long jump can do exactly the same thing. So it's not necessarily an improvement in that respect. Here's a much more interesting example, which is backtracking. Continuations are neat because you can actually call them more than once. Okay. which is strange when you first think about it, but it actually comes in handy, for example, in this kind of code. So if you have a continuation, you could store that continuation somewhere, global variable, whatever, and in your code actually call this continuation several times. So what you're doing is actually returning to the same place in your computation with different values. Okay? And we're actually going to take advantage of this. So let's say the problem is the following. We want to find a triple of values, x, y, and z. X, y, and z are between 2 and 9. And they must respect this equality, x squared equals y squared plus z squared. Okay, so one solution is actually 5, 3, 4, 5 squared equals 3 squared plus 4 squared. Okay? And we're going to express this search in the following way. We'll say that x is actually in the range from 2 to 9. Same thing for y, same thing for z. Okay? And then we'll test if the equality holds. And if so, we just return the list x, y, z. Otherwise, we call this fail function. And what fail will do is actually return inside these bindings and try the next possible binding. So when we say in range 2 to 9, it actually returns 2. The value of x will be 2. In range 2 to 9 will return 2. In range 2 to 9 will return 2. Okay? This doesn't hold, the equality doesn't hold. So fail will be called, which actually returns inside the in range here, and actually will return 3 as the value of z. Okay? And eventually, that doesn't work either, and we'll actually go off the end of the range here. And when this happens, in range actually is the one that's failing. Okay? It can't produce a new value. So because it's failing, it's actually trying to generate the next number from this oscillator range. So this time y will be bumped to 3, and we start over again. Here we start at 2. So basically this is a triply nested loop, x, y, and z going from 2 to 9. It's just expressed in a way that's sort of more declarative.
As inefficient as possible.
Yes. So as usual, backtracking is used by definition inefficient. So how can in range and fail be defined? It's actually not that complex. I mean, I shouldn't say complex. It is complex. It's just not very long. So the idea is that fail is actually a global variable, and initially it's a function that if you call, we'll say there's no solution possible. There's no choice point that can be retried. And this variable will actually be mutated in the code here, and the new function will be installed in fail, okay, which will resume the continuation when it's called. I won't go into all the details, but if you want to try it, it's really cool to try it out. Okay, so let's get on with the meat of the presentation. So this is how we'll go about compiling scheme to C in this particular compiler. And the idea is to use source-to-source transformations to do most of the compilation work. And source-to-source transformation is basically a small compiler whose source language and target language are the same language. So you do transformations, but you stay within the same language. And what a source-to-source transformation usually does is make the output a little simpler. So it uses less advanced features of the language, but still it stays within the same language. And this is what we'll be using. And in particular, there are two transformations that are necessary for a scheme-to-C compiler. Closure conversion, and it will tackle the problem of representing closures or implementing closures, and CPS conversion, which is more tackles the problem of implementing continuations. So here is the scheme subset that is targeted by the compiler. So in order to highlight the difficult parts of writing a Scheme to C compiler, there are a bunch of things that basically left out. So there are very few primitives that are supported by the compiler. It would actually be easy to add them, but I just have a small set that's large enough to make interesting, to write interesting examples. Plus, minus, signs, equal, less than, display, and obviously can't leave out CC, otherwise it's not too easy. The data types are exact integers and functions, and true and false will be represented by 0 and 1 to keep things simple. Only the main special forms of scheme are implemented. There are no macros. Assignment can only be done with local variables. Doing assignments on local variables actually adds another problem, which is actually quite easy to solve, but doesn't fit in 90 minutes. No variable errors in functions and no error checking in the compiler. So the exercise is to implement the rest of Scheme with this, once this is done. Okay, so let's look at the first problem of closure conversion. Well, the problem, closure conversion is a solution. The problem is access to free variables. So in this example, we have a function that takes three parameters x, y, and z. And in its body, it defines another function f with two parameters a and b. And this function has three variables. So it will access x and y, which are actually defined in the outer lambda. A and b are actually parameters that are, so we have bound occurrences here, a and b, and then free occurrences of x and y. So when this code is run, f is called twice. The values 1 and 2 for a and b, and then for 3 and 4. We have two columns there. And the question is, how can the values of x and y be obtained in the body of f? So I'll present two ideas of how this can be solved. The first isn't a general solution, but it works well in particular cases. And it's called lambda lifting. And the idea is basically that you take the variables, the free variables of the function you're calling, and you basically pass them in as parameters. So if you know that this function is going to use x and y as free variables, then you add that as x and y as parameters, and then when you call f, you basically pass x and y. Now the x and y here refers to the x and y of the outer lambda. Okay? And when you see x and y here, now they refer to just plain old parameters. So all the accesses here are to bound occurrences of variables, which, as I said, is something that's easy to implement. So that's all very fine, but it doesn't work in general. So if we just slightly change our original function to be like this, namely that instead of calling f, we actually return f. Okay? Here we can't do the same transformation. We can't do lambda lifting because the code that has called this function is receiving now a function that it can do just anything it wants with. So it can store it in data structures, pass it around in functions, and so on. And there's no way for these other call sites to actually know what are the values of x and y that are related to this particular function. Okay? So lambda lifting has its limits, and actually, since it's not a general solution, it won't be used in this compiler. So
Does lambda lifting has other uses that are really useful?
Oh, I mean, lambda lifting is typically compilers, Scheme or other functional languages use lambda lifting. Because for a lot of codes, it actually is possible to do lambda lifting.
Okay, so it uses it if it can prove that lambda lifting is...
Yeah, and it's actually very simple to test that,
Okay.
that it's possible. If you have a function, for example, the function f here, so if you have a function that's bound to a variable, a lexical variable, and all the places where the lexical variable is used is in the function call, and that's the case that you have here, then you can do lambda lifting. As soon as you have that variable that's used just as a reference, like we have here, so we're referencing f to get the value of f, then you can just say, well, lambda lifting is not possible in that case. In fact, that's what Gambit does. So a very simple analysis is sufficient.
Change the x in the lambda function that
If we change x
inside the lambda.
Okay, yes, that's another problem. That if you do something that's called assignment conversion, then that problem goes away. That's one of the reasons why in this particular compiler I only support assignments to global variables. It simplifies the problem quite a bit. So what we actually need is a closure. Okay, we need a data structure that actually packages up the information that is required by this function here, namely x and y. So we need to package up this information, and we call this a closure. So closure conversion can be done this way. So this is the same example, but converted to make explicit the creation of the closure. So here, f will actually be bound to a vector. Okay, here I'm using a sort of standard scheme terminology. So we're creating an object that has x and y as the second and third field, and the first field is actually a lambda. Okay. The lambda, where we've added a parameter that's called self. And the idea is that when this function will be called, self will always be a pointer to the vector that's been created here. Okay? So in places where you're calling a function, so this is the translation of the example where we had f applied to 1 and 2 and f applied to 3 and 4. Here, the f actually represents this closure, this vector. So by accessing the first field, we actually get the function here. And we pass f as a parameter, so self here will actually receive the vector. So within the body here, we can actually access in second position the value of x, and in second position the value of y. Okay, and this is basically closure conversion. Here I've expressed it with vectors. Okay, so we need a way of constructing the closure. So this is done with vector. We need a way to access fields of this structure, and I've done it with vector ref. We actually need to give this object a special type tag if we wanted to do some kind of dynamic type checking. So if we want to implement correctly procedure question mark, then this wouldn't quite work. But essentially the idea is of packaging things in a closure is zero value. Now if you do this thing, you'll notice that there are no free variables in this lambda. Okay? And if you do closure conversion in a systematic way over your program, then all of your lambdas have no free variables. So it eliminates the problem of free variables. So here are the rules for doing closure conversion. There are 3 rules. And I've expressed the rules in the following way. when you have code that's within a box, it means this is code that hasn't been converted yet. And this means the conversion of this code is equal to this code that we have here. So if we're converting a lambda expression, so if we're closure converting a lambda expression, we add a self parameter, okay, and we create the closure with the closure vector, and the body of the lambda will also have to be closure converted, and all of the variables here, these are the three variables of the lambda expression, also have to be closure converted. If within the code we find a free variable, that we replace that with the vector ref of self, and the index that we use is basically the position of that variable within the list of free variables of the enclosing lambda expression. So if we have a function call, that's the last thing we have to change. If we do a function call with a certain number of parameters, then, as I said before, we extract the function that we want to call. Okay, so we extract the first field of function f. We pass f as parameter. Okay, so this will match the self parameter here, and then we closure convert all the expressions also. Okay, in the compiler I wrote, I could use closure instead of vector, and closure ref instead of vector ref, and these are just primitives that are specific for the closure representation. But essentially, they play exactly the same role as vector and vector ref. Okay, so is that good? Closure conversion is simple when compared to CPS conversion. So let's see what the problem is with what we're trying to solve. So continuations have indefinite extent because we have call CC in the language, and as we saw in one of the examples, the continuations can be invoked more than once. So we can't retain continuations when a function returns, as is done in most languages. And it has to be up to the garbage collector to actually reclaim continuations. So the simple solution that we're going to adopt is to transform the program so that all continuations are actually objects, namely closures, and the garbage collector will be in charge of actually reclaiming these objects. So if we find a way of actually representing the implicit continuations of the program, making them explicit with closures, then the problem goes away, because then it's the problem of the garbage collector to reclaim these objects. So that's sort of the basic approach here. So how can we do that? Well, remember that a continuation represents a computation that is awaiting a value before the computation can continue. So when an expression is evaluated, the expression is actually the producer of information, namely the result of the evaluation, and the continuation is the consumer of this information. So we have these two things, the producer of information, the consumer of information, and we can express the communication of the result simply by doing a function call. So in the transformed code, we'll be using function calls to actually represent returning to continuation with a particular value. Okay, let's do an example. Here's fragment of code, the function called square, takes a parameter x and squares it. And we use this function in the call to write of the sum of square of 10 and 1. So let's try to figure out what is the continuation of the call to square of 10. Well, the continuation has to receive the result of this call, add 1 to this result, and write the result. So actually we could represent this continuation simply with a lambda expression. So a lambda expression that takes r, the result of the call to square of 10, and it simply writes r plus 1, and this represents the continuation. So if you understand this, we're halfway there. Now that we have a representation for continuations, namely a closure, we have to have a way of actually communicating this continuation to the function we're calling. So how can we do that? Well, basically we can add a parameter to the function. And this is why we call this continuation passing style. When we translate a function call, what we really want to do is pass the continuation to the function we're calling. And it will be up to that function how it uses this continuation, how it returns information to the continuation. So here is how we could translate the example. We've added a parameter k, which will represent the continuation for the function square, and we use this function, this continuation, simply in the function call. So we do a function call to k, passing as a result the square of x. Okay, so this actually represents returning from square with a particular value. And when we call square, we obviously have to provide the continuation for square. So this is exactly the expression we had before. So we're passing a function that will receive the result, add 1 to it, and call write. And by doing so, we give this continuation to square. Square uses that continuation to call back with the result from the call to square. Oh, il faut changer. We could take a break actually. I think they have to change the tape or something.